Every picture you've ever seen of Mars shows a rust-coated, frozen desert, a sterile world where nothing has moved for 3 billion years. But beneath that quiet layer of red dust sits the crime scene of the greatest robbery in solar system history. Mars wasn't always a barren wasteland. It used to be Earth's blue twin, complete with torrential rain, deep oceans, a protective magnetic shield, and river valleys carving through its continents. So, what murdered a whole planet? Where did an entire ocean go? And why are NASA's latest rovers finding signs that Mars might still be alive beneath its skin? Today, we are reopening the coldest case file in planetary science. Let's get into it. If you could take a time machine back roughly 4 billion years to the early days of our solar system, standing on Mars wouldn't feel alien at all. In fact, if you looked out the window of your time capsule, you might actually confuse it for Earth. Back then, during an era geologists call the Noachian period, Mars was a thriving blue world. Data collected by NASA's Curiosity and Perseverance rovers, along with orbital mapping from the Mars Reconnaissance Orbiter, MRO, paints a picture that shatters the myth of Mars as a lifelong desert. We're talking about a planet with a thick, insulating atmosphere dominated by carbon dioxide and water vapor. Temperatures were warm enough for liquid water to rain down from the sky, fill massive crater lakes, and cut winding river networks across the southern highlands. Take Gale Crater, where the Curiosity rover landed in 2012. For years, scientists debated whether the clay minerals and layered sediments seen from space were formed by water or volcanic activity. Curiosity drove right up to Mount Sharp, drilled into the mudstone, and settled the debate permanently. The rover was literally rolling across the dried-up bed of an ancient lake system that persisted for millions of years at a time. Even more dramatic is Jezero Crater, the current playground of Perseverance. Satellite imagery showed a massive fan-shaped geological structure spilling into the crater. When Perseverance inspected the rocks up close, it confirmed what sedimentologists suspected. It's a textbook river delta. Billions of years ago, a raging river punched through the crater wall, carrying mud, gravel, and organic compounds, depositing them in a calm, deep lake. According to peer-reviewed models published by NASA scientists, the northern hemisphere of ancient Mars was likely covered by a vast, continuous ocean containing more liquid water than Earth's Arctic Ocean. So, if early Mars had lakes, rivers, rain, and a warm blanket of air, why does it look like a global salt flat today? What went so catastrophically wrong? To understand the death of Mars, you first have to understand how Earth stays alive. Right now, beneath your feet, Earth has a churning inner engine, a superheated, liquid outer core made of molten iron and nickel. As Earth rotates, this convective soup of molten metal acts like a giant dynamo, generating a massive, invisible magnetic bubble around our planet, the magnetosphere. This magnetic shield is Earth's primary line of defense. It deflects the solar wind, an endless stream of high-energy charged particles constantly blasted into space by the sun at 1,000,000 miles per hour. Without our magnetosphere, the solar wind would strip away our atmosphere, dry up our oceans, and blast the surface with lethal radiation. 4 billion years ago, Mars had its own molten iron core and its own global magnetic field. We know this because planetary scientists mapped remnant magnetic signatures locked in the ancient crustal rocks of the Martian southern hemisphere. Then, Mars hit a biological limit imposed by its own size. It has only about half the diameter of Earth and just 10% of Earth's total mass. Basic thermal physics dictates that smaller objects cool down much faster than larger ones. Because Mars was so small, its internal heat dissipated rapidly. Around 3.9 to 4.1 billion years ago, the core cooled down enough that the convective motion of its molten iron slowed to a crawl. The Martian dynamo stalled, the planet's magnetic shield collapsed, and that is when the solar wind descended on Mars like a cosmic butcher. Without a protective magnetic field, the upper atmosphere of Mars was left completely exposed to the energetic particles of the Sun. Over hundreds of millions of years, solar radiation hit atmospheric water molecules, breaking them apart into hydrogen and oxygen. The light hydrogen gas escaped directly into deep space, while the solar wind stripped away the heavier carbon dioxide brick by brick. This stripping process was directly measured and confirmed by NASA's MAVEN spacecraft, Mars Atmosphere and Volatile Evolution, which entered Martian orbit in 2014. MAVEN caught the solar wind in the act, measuring the exact rate at which Mars is still losing its atmosphere to space today, roughly 100 grams of gas every single second, spiking wildly during solar storms. As the atmospheric pressure dropped, the water on the surface reached its boiling point at freezing temperatures, evaporating into gas and getting swept away by the solar wind. Within a few 100 million years, the lakes dried up, the sky thinned out into a vacuum, and Mars froze over, becoming the red ghost we see today. Before you write Mars off as a completely frozen corpse, stop. What if I told you that everything I just described, the lost oceans, the dead core, the stripped atmosphere, is only half the story? In 2018, NASA put a stethoscope against the ground of Mars, and what it heard wasn't the silence of a dead world. It was a heartbeat. High-tech seismometers buried in the red dirt are picking up deep quakes, liquid reservoirs trapped miles beneath the surface, and massive clouds of methane gas mysteriously breathing out of the ground at the exact same time every year. Mars is not dead. It's hiding, and what's buried beneath the dust might change human history forever. For decades, planetary geologists operated under a single assumption. Mars has been geologically inert for at least 2 billion years. No earthquakes, no volcanic activity, no liquid water, no thermal activity. Just a giant cold rock floating in space. Enter NASA's InSight lander, which landed on the flat plains of Elysium Planitia. Unlike Curiosity or Perseverance, InSight wasn't built to drive around taking pictures of rocks. It was built to do one thing: drop an ultra-sensitive French SEIS seismometer onto the dirt and listen to the interior of Mars. Over its multi-year mission, InSight recorded over 1,300 distinct Marsquakes. Some were caused by meteorites smashing into the surface, but the vast majority were caused by something far more shocking: tectonic fracturing and active magma movement in the Martian mantle. Specifically, many of the largest quakes originated from a geological region called Cerberus Fossae, a network of massive, parallel rifts in the crust. Analysis of data published in Nature revealed that Cerberus Fossae is a geologically active volcanic zone. Warm mantle plumes are actively rising beneath the crust, breaking rocks and generating volcanic heat today. Mars isn't cold inside, its heart is still lukewarm. And where you have internal heat trapped beneath a frozen crust, you get the holy grail of planetary science: subsurface liquid water. In 2024, a landmark study published by scientists analyzing InSight's seismic data calculated that there is enough liquid water trapped in the porous rock of the middle Martian crust, between 11 and 20 kilometers down, to fill a global ocean miles deep. Because the surface is a freezing vacuum bombarded by harsh ultraviolet radiation, water on the surface evaporates or freezes instantly. But down beneath the crust, shielded from radiation and warmed by residual magma, liquid water is sitting in darkness, creating an environment that has stayed stable for billions of years. And then there is the methane mystery. Since 2004, ground telescopes and the Curiosity rover have been detecting spikes of methane gas in the Martian atmosphere. But here's the kicker. Curiosity discovered that methane levels fluctuate seasonally. Every Martian summer, methane gas spikes. Every winter, it disappears. On Earth, over 95% of atmospheric methane is produced by living organisms, microbes, farm animals, and decaying organic matter. On Mars, methane could be created by geology, a process called serpentinization, or microorganisms living in deep underground aquifers, releasing gas that seeps out through seasonal cracks in the dirt. We don't know for sure yet, but one thing is clear: Mars is breathing. This brings us to the ultimate question. If Mars was once a paradise and its interior is still kicking, can humanity bring it back to life? Can we call Mars home? Humanity's relationship with Mars is transitioning from simple observation to active colonization planning. But colonizing Mars isn't as simple as building a dome and stepping outside in a sweater. The challenges are terrifying. The atmosphere. The surface pressure of Mars is less than 1% of Earth's. If you stepped outside without a pressure suit, your blood wouldn't boil like in movies, but the moisture on your lungs, tongue, and eyes would instantly evaporate, and you'd lose consciousness in 15 seconds. The radiation. Without a global magnetic field or a thick ozone layer, the surface of Mars is constantly fried by galactic cosmic rays and solar particle events. Spending a year on Mars unprotected exposes an astronaut to radiation levels hundreds of times higher than on Earth. The poison dust. Martian soil is packed with perchlorates, toxic chemical salts that destroy thyroid glands and make growing standard Earth crops directly in the dirt impossible without chemical washing. Yet, despite these nightmares, Mars remains the only planet in our solar system where humanity could realistically build a self-sustaining second home. We already have the blueprints to solve these problems using NASA technology. We don't need to ship water from Earth. Glaciers of pure ice sit just a few feet below the surface dust at mid-latitudes. Future astronauts can simply heat the ground, collect the steam, and process it into drinking water and rocket fuel, methane and liquid oxygen. In 2021, the MOXIE experiment on NASA's Perseverance rover successfully proved that we can pull carbon dioxide directly out of the thin Martian air and strip it down to create pure, breathable oxygen on demand. Instead of building glass domes on the surface like in sci-fi movies, early Martian pioneers will likely live inside giant subterranean lava tubes, massive natural underground tunnels left behind by ancient volcanic eruptions. A few meters of Martian dirt overhead provides total shielding from cosmic rays, radiation, and micrometeorites. Terraforming Mars, rebuilding its atmosphere, melting its polar ice caps, and restoring liquid water to the surface would take centuries of industrial effort. Every rock drilled by Perseverance, every earthquake mapped by InSight, and every sample cached in Jezero crater for the upcoming Mars sample return mission is a small step toward answering the ultimate question. Are we a single planet species destined to fade away, or will Mars become our stepping stone to the stars? Mars is a mirror. When we look at its dry riverbeds and lost magnetic field, we are looking at a warning of what can happen when a planet loses its vital systems. But when we look at its buried glaciers, deep quakes, and complex chemistry, we see a world of endless potential waiting for its second act. Mars isn't just a dead twin floating in the dark. It is our past, our warning, and very likely our future. Thank you so much for watching. Do you think humanity will land footprint boots on Mars before 2040? Or are the risks of radiation and logistics too high? Drop your thoughts in the comments below. I read every single one. Thanks again for hanging out. Stay curious, and I'll see you in the next one. Bye.